Welcome to another episode of Complete Developer Podcast, the podcast by coders for coders about all aspects of creating your best life as a developer.
I'm Will, the accomplished developer and aspiring software architect.
And I'm Beej, the journeyman developer, sharing my journey in development.
Complete Developer Podcast is supported by listeners like you. We are now on Patreon at www.patreon.com/Complete Developer Podcast.
If you're a developer using a compiled programming language, your craft kind of depends on your compiler. Computers are not capable of natively understanding any of your code. Instead, the machine must be told what to do in a way that it understands. Depending on your language and platform, to do this, you may find yourself relying on either a compiler or an interpreter. In this episode, we're going to talk a little bit about how compilers work. While you can be a reasonably successful developer even without understanding this, if you really want to become a highly skilled software developer, you'll need deeper knowledge about what is going on behind the scenes. This episode will sort of lay the groundwork for you to get started on that deeper dive. But before we get started, Will, what have you been fighting this week?
Well, dude, the book manuscript is done. 242 pages. Yes.
I know. That's awesome.
And now the edits happen, and editing is supposedly worse. But I have an editor, right? So I'll just have to go in and approve the edits and maybe fix a few things, and there's back and forth. I'm sure it's going to take an age to get it done, but at least the manuscript is out of the way. And then, so like Tuesday, I was like, okay, I kind of chill out a little bit, and then I started like working on the SEO of our website and figured out that we weren't showing up in Google Search Console. It never crawls. There's all kinds of stuff that was screwed up. So I had to go in and fix that. And I'm still waiting to find out if I actually fixed it. And then last night I was like, I could totally chill out. I got the book done and I realized, I got to write a show outline for tomorrow. So I still have not really relaxed, I guess is what I'm getting to. How about you?
Well, I completely understand that. This week has been crazy busy. The semester is ending at school, so I've been studying a lot. Not really as much as I'd like, though. I don't feel like I'm studying at the level that I used to study at, if you know what I mean.
Yeah, you don't have the neuroplasticity in the free time.
The neuroplasticity I have, the free time I do not. Also, work has me pretty busy, too. So we're kind of finishing one project. So they've put me on a bunch of smaller things, either advising or building like a little piece here, a little piece there. So it's kind of got me bouncing all over the place. I have gotten to build some pretty cool stuff in .NET Core though. However, it all takes a back seat if a bug is found in the one that's about to go out. So it's that attitude of I don't want to get too deep into it because I know at any point I could be pulled out.
Yeah, I'm fighting a lot of that too. I know the feeling.
Now, in better news, I'm getting ready to head down to my sister's for Easter, which is this coming Sunday. This is coming out several weeks after that, but it's going to be a lot of fun. I get to see her and my nieces, though I do have to ride for 8 or 9 hours in a car with my mom.
So is that entire trip in states that have laws against open containers?
Well, Tennessee doesn't. I'm not sure about Georgia or Florida. I don't think Florida does. So
now you need to do some legal research quickly.
Yes. But anyways, my sister texted me the other day asking if I'd like to go to a concert. And I'm thinking, it's probably, one of the kids at school. I probably would have known if it was a niece or something. But anyways, I was like, yeah, I love concerts. What kind of show is it? And she's like, Garth Brooks. As if I should have known this.
Right.
I'm like, apparently, my mom knew that they had tickets to the Garth concert and knew that we're going to be watching the kids while they go. I wasn't informed of this, but they have an extra ticket. So guess who gets to go see Garth?
Your mother.
No, me.
There you go.
Yeah. Mom doesn't like concerts. She's like you when it comes to crowds.
Yeah.
But of course, obviously I said yes. He was my favorite musician as a child. Now, when I got to my teen years, that led to Tom Petty and Metallica. Don't ask about the combination there. It's unique, and I was a really strange child and teenager and adult. Anyways, I'm really excited about getting to see Garth again. But speaking of seeing, I have something for eyesight in IoTs. One step closer to Geordi's visor in Star Trek, eSight is a way to help the visually impaired see things that they normally couldn't. It works by capturing high-quality video and displaying it on 2 high-resolution screens, one in front of each eye. This footage is also enhanced by custom optics and sort of a special algorithm designed specifically for the wearer. It allows people to live out normal lives, enjoy their hobbies, and even see their loved ones again when their eyesight goes bad. It is rather expensive, though they do have a payment plan, and it's probably around the same or less than optical surgery in a lot of cases. While not exactly Internet of Things, I just like that this is a really unique way of using technology to enhance people's lives. I thought it was really cool. Really creative way of doing that. And I'll have a link to it in the show notes if you guys want to check it out. If you know someone with impaired vision that might benefit from this, you can send them the link. Who's talking to us this week?
Well, we got tagged in a tweet from John Folder saying days 24 through 31 of 100 Days of Code. I've been hard at the coding, but slow on the tweets. Been working on learning React hooks, integrating with MongoDB and Next, surfing all the great waves. Autumn is the best. Catching up on my favorite podcasts at Syntax FM and at Complete Dev Pod.
So, John, thanks so much. Given that you're talking about autumn and it's April right now, I'm guessing you're somewhere in the southern hemisphere. Surfing, I'm going to go with Australia. So,
or he just read the Angular documentation and got so confused he doesn't know which hemisphere. So it could be that.
Well, there's that. Yeah,
it has that effect.
Yeah, Australia is on my places to visit, but realistically, where isn't?
Yeah,
I like to travel, as you guys know. I haven't traveled as much as I would love to, but there is a big list of places I do want to go. John, really, though, thank you so much for listening. We really appreciate that. Send us a direct message with your contact information because we've got a Complete Developer water bottle just for you. Guys, if you'd like your very own Complete Developer water bottle, leave us a review on iTunes or comment on the website or any of our social media. We post all of our episodes to Facebook, Twitter, and LinkedIn. We're also on Instagram and Tumblr, though I haven't posted very much on those, so I'm going to try to get back to that. Check us out each week on Facebook Live. We talk about what's going on in the tech world and answer some listener questions. We're going to be expanding our live show since we just got Restream, and we're going to see what other platforms we can get into and how we can better be out there for our audience. Or you could join the conversation anytime via Slack by going to slack.completedevelopernetwork.com.
Compilers are required tools for software development. Essentially, a compiler translates your written code into something that a machine can use. Most of the details of this episode come from the book Compilers, Principles, Techniques, and Tools, which has 4 authors. Mm-hmm. We're not going to list it out. It's an excellent book for deeply understanding how compilers actually work under the hood in detail. You may have heard this book referred to as the Dragon Book because of its over-the-top, really awesome cover. This book is how I learned the most about compilers and is much more of an in-depth discussion than we can possibly cover in an episode. It's right at 1,000 pages. Yeah, it's like, the book has gone from like reading size to like beating people size. It's like Bible size. You can definitely smite someone with it.
Oh, if you ever want to get me a book, you can do that, right?
Right. Or maybe one of the audience can.
Yeah, well,
there we go.
That's true too.
You never know what'll happen.
So we're going to start off with a few definitions, and by a few, I mean quite a few.
I trimmed it as much as I could.
Yeah.
That's all I'm going to say. It's just, there's a lot of stuff that you kind of need to have in place to understand why this is a problem before we get into how this problem got solved. So the first thing and the most obvious definition is, what is a compiler? And a compiler is a program that can read a program in one language, that would be the source language, and translate it into an equivalent program in another language, that would be the target language.
So I see 3 definitions in there: compiler, source language, and target language.
Right. Yeah. I mean, you have 2 different languages going on, and then something that transfers from one to the other, usually down to a closer to the machine version of it.
So speaking of that, the next definition is a high-level language. This is a language with a strong degree of abstraction from the details of how the computer operates. So an example of this would be like C++, C#, Visual Basic, Python.
Right. There's loads of them. Ruby, SQL. But the other thing that a lot of people might be surprised to see is C++, because, well, you got to deal with memory management, but you're not really dealing with it. You're dealing with, C++'s wrapper around it. It's a lot different further down. That's why it would be called a high-level language.
Now, the next one is a low-level language, as opposed to a high-level. And this is a language that provides very little or no abstraction from the computer's instruction set architecture. An example of this would be assembler. And I've been learning a little bit of that in the course I'm in this semester. Not very much. It's not very, very heavy into it, but just a little bit. We actually started off even lower than assembler. But yeah.
It's a completely different thought space, right? Like I took one of our projects at a job I had in college, and I wrote a C++ program with inline assembler in it and sped a process up by 3,750%. And that was in a debug build too. And that's neither here nor there, but like it is a weird way to code in a lot of respects.
What's really funny is when it came out, it was an
improvement.
Yeah. It was the, hey, here's how we can make this human readable. So that's try to wrap your brain around that, especially if you don't have a CS degree and haven't messed with this or learned about it much. This really low level stuff that looks like a bunch of nonsense was, when it came out, considered the easy human readable version.
Yeah.
So
we dropped another definition in that previous one, which is the instruction set architecture. And this is essentially an abstract model of a computer. And this defines everything that a machine language programmer needs to know to program the computer.
These define things like the CPU registers, main memory, how the memory is addressed, and things like that. This is the stuff that I'm learning in the class I'm in right now, or have been learning. I'm studying for the final now. But in a future episode, we're going to kind of talk more about this. Either Will is going to write it from his experience in school, or I'm going to write it from my recent experience in school.
Yeah, it may be better for you to do it, because when I did it, it was 16-bit.
No, that's what I learned too. Is 16-bit.
You did too?
Yeah.
Well, maybe it won't be so bad then.
Yeah, I mean, it's. I have this book. Our textbook is The Elements of Computing Systems: Building a Modern Computer from First Principles, and it's a really good book. The great thing about this is, like, if you follow along, like you read each chapter, and Will can see my highlights in it, but if you read each chapter and you do the assignments, by the end of the book, you have built basically a computer.
Yeah.
From the ground up.
So the next definition is machine language. And machine language is built up from discrete statements or instructions, and this is per Wikipedia. An instruction may specify the CPU registers in use, an operation occurring on the contents of the register, and a memory location. These may include logical operations, arithmetic operations, control flow, all that kind of stuff. Now, let's talk about what a register is. A register is a quickly accessible location in the CPU of a computer. This is faster than your main memory. It's faster than anything else pretty much that you've got. It's also very, very small. So Like most systems will load data from memory locations into registers, do operations on the contents of the register, and then move the data back into memory. In fact, I can't think of any architecture that I've ever seen that's done otherwise. This process, by the way, is why it's faster. If you have something in a register and you need to clear the register and set it to 0, it's faster to XOR the register's contents with itself than it is to pull a 0 out of memory and put it in there.
Yeah.
Registers are usually referred to by their size, which is expressed in bits. So when I was talking about 16-bit assembler earlier, that's what I was talking about.
They're also usually named. Like modern x86 architecture will have several duplicates of a lot of their registers for the purpose of performance.
Right. So if you've got a EAX register, you actually have several different registers that you're writing to when you're putting stuff in there. And the CPU kind of can do some speculative execution. It can do a lot of other stuff to optimize getting stuff in and out of the processor in parallel. And that's why that's there.
Yeah, there's a lot about this in my textbook from the semester on how to read and write from a register and how the register reads and writes from memory and stuff like that.
So the next thing to talk about real quick is the memory addresses. And memory addresses are references to a specific location in the computer's memory. They're usually unsigned integers of some size or other. Whatever the OS supports, whatever the hardware supports, that's kind of how that would play out. Now, the next piece we're going to talk about is the stack. And the stack is a data structure that stores information about the active subroutines of a computer program. Again, this is from Wikipedia. Essentially, when you call another function, relevant variables from your current function are pushed onto the stack. And this will also include a pointer to the location in memory of the currently executing instruction. Next, instruction proceeds to the memory location when the function you called begins. In other words, it jumps down and says, okay, here's the next piece we're doing. It goes through it. When it returns, the stuff is popped back off the stack and you basically restore your previous context. This, by the way, is how things like buffer overflows get you, is because you can actually overwrite a stack frame in some cases.
Yeah, the book that I've been using as a textbook has really great, drawn out process to follow. There's also some really great YouTube videos that I've had to watch from class that are they're freely available because they're on YouTube. So if you watch those, dude, you will see that we are simplifying the ever-loving daylights out of this. There's a lot more going on, especially when you start looking at what's happening, at the processor level. Oh yeah. There's a lot down there, and I watch those videos when I'm at the gym on the treadmill. So it's either watch a school video or watch the TVs.
It seems like you would put the assembler video behind you so you can run away from it. That seems like that's how most people would react to that.
Yeah. So getting back to the stack, once everything is done, the previous address is kind of popped off the stack and execution goes back there, and the relevant variables from the previous call are also popped off the stack.
And the relevant variables, by the way, it might not be like a string, right? It's probably a pointer to the beginning of the string. It's lower level. It's not, hey, here's a kilobyte of crap that's on the stack. It's no, here's the start of it, and here's the length, maybe.
So the final definition we're going to talk about is compiler passes. Compilers can either be single pass or multi-pass. Lilu Dallas, multi-pass.
That's what I was thinking. Multi-pass.
So single pass compilers are usually a lot faster. And a lot of your earlier ones are single pass. Think like Pascal.
Yeah, Delphi, I think, still is.
I miss Pascal. Sure that was one of my favorite classes I took in high school. Now, the Lilu Dallas multipass compilers go through the process several times and are advantageous for more advanced optimizations of the compiled code.
Right. So essentially, and we're going to get into this here in a bit, but basically it hits it repeatedly to trim down the amount of code it has to execute. So let's talk about why you need a compiler.
Yeah, why would you need a compiler? Come on.
Yeah. Man. I mean, can't you just get a really, really small magnet and mess with the bits yourself? No. So we really, really simplified the explanations above. Every one of these things has got a huge Wikipedia page that's linked to a bunch of other huge Wikipedia pages. Like it's terrible how much is actually going on there. Programming in assembler or another truly low-level language is a lot harder to reason about for most people. You know, if you're going, okay, I want to make the machine do this thing, it's great. If you're going, I want my program to do this thing and, you know, get the machine to do it for me, that's a little trickier. It really feels, honestly, like my feeling on assembler is it's almost like programming by side effect. Like I made the machine do something and set it in a certain state, and then I got the result as a side effect of what I told the machine to do, not because I implicitly told the machine to do it, if that makes sense.
Yeah, I follow what you're saying.
It's like a bank shot, or, you know, it's just a really, it's really difficult, especially when you're doing something really complex, to do it in assembler. So the hardware that your code runs on is going to vary quite a bit, especially at the lower levels. And you really want a layer of abstraction around that so that you can write a program and have it run on other computers.
Well, that was the whole thing with assembler when it first came out, was that you had one language that you could write that would compile to the machine language on different computers. Because before that, you had to write it for the specific processor that you were doing, and not just the specific like brand, but the model, the version of and that model,
chipset, and all that kind of fun stuff.
Yeah, like it had to be super, super specific. And so that was the great thing about assembler is, oh, hey, now we don't have to do that. We can write it in one language and then have it compile down to whatever chipset it needs to be on.
Yeah, and then we started complicating our chipsets.
There's that.
I mean, it's like we do this every little while in computing, right? Like you even have languages now that can compile down to different versions of JavaScript, right?
Yeah.
Or ORMs that compile down to different SQL, stuff. Like this is never going away. We really like our abstractions, and you can really optimize lower level code a lot. But it takes a lot of time, and a lot of optimizations are more easily done by a tool instead of a person, because the program can do a lot of things automatically. And, the other fun thing that makes this more complex now, especially, is that processors can do multiple things at a time. And this is really hard for people to reason about just in general. So that's another thing that's going to be in the mix.
Well, it's multi-core processors, right?
Right.
That's what you're talking about. Yeah. So,
multi-core, and then you've also got you've got all the scheduling of when stuff goes into the processor.
Right. So it seems like it's doing multiple things at a time, but like it's really each core is only doing one thing at a time. It's just so fast, and it's going between different things that
and you've also got some other weird bits, right?
Yeah.
You've got speculative execution going on. You've got branch path prediction. There's a lot of stuff that if you or I had to write a for loop and just put it on the CPU, we would have a really hard time getting that right and doing anything with it.
Yeah, there's so many layers of complexity. It's kind of what I was getting at, is that it is just that you want that abstraction so you don't have to deal with it.
Yeah, you want a mental model that works with what you're doing. In other words, if the CPU scheduling and stuff is your problem, you really want it to be your only problem.
Yeah, that's true. So next, we're going to talk about the compiler front end. The front end of the compiler is responsible for analyzing the source code to build an internal representation of the program. This includes building a symbol table, which maps parts of the source code to information associated with them.
Right, and this is usually broken into 3 phases. So the first one is called lexing, and that's basically where it looks at your code and it breaks that sequence of characters into a sequence of tokens, which are strings with an assigned and an identified meaning.
Next is syntax analysis, which converts the sequence of symbols or tokens and turns that into a representation of the code as an expression, usually in a tree form. This is called a parse tree.
Right. And the idea here is, they do that first phase to clean stuff up essentially and kind of make it easier to build that parse tree out of it. So these are just, phases that are easily proved correct. And that's why it's structured the way it is.
Yeah, those first two phases are where you get a lot of your linting too, and where you can get your red squigglies or whatever, depending on your IDE.
Right, like your syntax errors and stuff come out of there. A lot of those do. The next one is the semantic analysis, and this adds semantic information to the parse tree and builds up the symbol table. So this is like where your functions and stuff are, where your variables are, what they're called. It kind of builds all those references up so that the rest of the process can proceed faster. Now, this also does a lot of your type checking, object binding. That's where you say, okay, I have this thing being assigned to this property, this object. How does that really happen? That sort of stuff gets set up. And this varies a lot depending on the language in use. This is also when really incorrect programs start getting detected in a lot of cases. I mean, you'll have like your big syntax errors, and then you'll have other things like type issues that come up later. This, by the way, is why a lot of times when you're typing in your IDE and you really screw up, you get a set of errors. And then if you fix those, you'll get another set of errors. You've gone to another phase of the front end of the compiler, if that makes sense.
Yeah, that does. So the front end may be preceded with a pre-processing phase that handles things like macro substitution, conditional compilation constants, those types of things.
Right. And so this would be, you don't see it as much in like C# and languages like that, but you will see conditional compilation constants sometimes, especially if you're looking at situations where you've got like that pound if to say, okay, this is running in Silverlight versus this is running in regular .NET, and you change the statements you're using, and then you'll set those before you run through and compile. And so you can make different versions of the program for different architectures with that. That happens obviously before the rest of this happens because it changes the actual code that's evaluated. So the next phase is called the middle end because somebody, I don't know, I think somebody was probably delirious when they decided to call it that. So that's a thing. And the middle end of the compiler.
Wait, you didn't make that up. Somebody else made that up?
Somebody else made that up.
Wow. Okay. I thought you were being silly there when I read this outline.
Nope. It was somebody else.
Wow.
Somebody really smart.
They were probably being silly. Like we know some really smart people that are that level goofy.
Yeah. Or, calling a defect a bug.
Yeah.
Right.
Well, that was because they literally found a
but it was a back reference eventually. Right.
Yeah.
So the middle end is responsible for optimizing the intermediate representation that's produced at the front end. So you get that parse tree out and all the annotations and stuff that are hanging off of it. And this usually has a couple of steps. And the first one is analysis. So it'll apply a bunch of different approaches here, but the goal is to find operations in that parse tree whose complexity can be reduced. Mm-hmm. And the next thing is actual optimization, where you actually apply those things. And so you have this structure of essentially expressions in that parse tree. And you go, hey, this thing is adding two constants, for instance. Yeah. Let's fix that and just put the actual value up there. And so, let's talk about a few of the things that might happen when this goes on.
So inline expansion, which replaces a function call with the contents of the function. This saves a jump or a stack allocation. It basically turns a functional or object style into procedural, where it pulls that and puts it in there.
That's right? One way it'll do. The other thing it will do is just go, hey, this is a little bitty function. Instead of having to jump, let's just copy the code.
Well, okay. So I didn't say that that's what it does for smaller things. I didn't emphasize that. I was more focused on what it does, not that it only does it with the smaller things. But yeah.
Yeah, the best way to think about this is almost like having a crappy programmer on staff that copies and pastes code, right? So that it's all right there. That's what this is doing for you, but it's it's not affecting the readability of the code. It's just making it simpler for the machine to deal with because it doesn't have to do as much stuff. This is also one of the things that you and I were talking about the other day. You got burned by the optimizations in C# compiling, and some stuff wasn't hitting breakpoints because they weren't there.
Yeah, so it was .NET Core. That was the interesting thing, is it was defaulting to the release build in my test cases. So when I tried to debug a test case, it had the optimized code set, which was creating these inline expansions. And so I wasn't able to hit those. And I was not able to actually see what some of the values were because they weren't available for the debugger to look at. It was really frustrating. It's one of those things that I was like, really, that doesn't do this in your regular .NET, but .NET Core, you have to go in there and manually set it to not do that. It was kind of annoying, but
it was amusing though when you sent me the message, because I was like, "Oh yeah, I know what that is."
Yeah,
because I've done enough stuff where I've been hit with that, and like I just don't trust any compiler optimizations when I'm debugging because of that sort of thing.
Well, yeah, and the thing is, my problem with that was I didn't know that optimization was on, because in your .NET framework, full framework, when you're running the Microsoft Test Suite, it runs it in debug mode where that is default off.
Right.
But with the MS Test in .NET Core, which is basically the same thing, but it's their .NET Core version, it runs it in whatever it's set to, so it doesn't change it to debug for the test purposes. And so it was running it in release where all that stuff was turned on. I had to go in and manually shift it over to the debug mode where that was turned off.
Yeah, and that's a really frustrating experience because I've had it so many times. It's just and another one that'll happen, and this is something that even your debugger is going to have this cleared out, and that's dead code removal. So like if you're returning and then you're looping after that never gets called. It's heuristically unreachable.
That's very good. And like in the .NET world, Visual Studio will actually tell you when your code is unreachable.
Right. These are the warnings that come out of the the front end, the middle of the front end.
Yeah. It's that syntax analysis part. That it's running that without you having to run the code, and it says, hey, and I think a lot of your IDEs will do that. Things like Notepad++ and Visual Studio Code may not, because they're not IDEs, they are editors.
Yeah, the compiler will usually kick it out if you put the right switches in, and that's how the IDE gets it most of the time. But that can be a little bit of a surprise, especially, I use ReSharper, and so it screams at me every time I do something like that. So I get, that's fixed.
Now, the next one is what you were talking about earlier in this point, which is constant propagation. If an expression is composed entirely of constants, then it just replaces it with the constant.
Right. So like if you have two variables and, one of them's, called A and it's set equal to 2, and you got another one called B and it's set equal to 3. And then you're setting another variable and you're saying, hey, we're going to call this one C and set it equal to A plus B. Instead of doing that operation at runtime, it's just going to put a 5 in there. That's basically what this does. It, depending on the language and depending on a lot of things, it may be fairly complex to the degree that it does this kind of stuff. So the next thing that can happen is called loop transformation. And there's a ton of stuff that happens here. This includes optimizations to break a loop into multiple loops, to bring inner loops to the outside in some cases, where it reduces the load on the CPU. A lot of this is done for performance, and we'll probably just have to write an episode on this. I will tell you that this is very, very important because most program code actually happens inside of a loop. With all of your apps, basically, if they're waiting for input, that's a big honking loop right there. And so anything you can do to optimize loop execution is really, really valuable for a compiler.
Yeah, I do think we have an episode on the thing for loops. I know we have one for sorting algorithms. So
yeah. So the final one that can happen, or at least another big one, is automatic parallelization, and this is what it does is it converts sequential code into parallel code so that multiple parts can execute at the same time. So like you fire something off and you go, hey, get me this file and open it up. Well, if there's another step right after that isn't dependent on that one can be kicked off while you're waiting on the hardware to come back. And so it'll do a lot of scheduling type actions in there for this.
So finally, we've made it to the back, and we're going to talk about the back end. This is responsible for CPU architecture specific optimization and for actual code generation. So there are two main phases here. Machine dependent optimizations, such as peephole optimizations, which rewrite short sequences of instructions into more efficient instructions.
Yeah, and you would see this a lot, especially like with older processors. For instance, where people would manually calculate, square roots, for instance. And it turns out that, hey, this one processor has got the ability to do that itself with a single instruction, and it all happens on the chip instead of you manually pulling stuff in and putting stuff out and trying to do it your way. It was the same kind of thing with dealing with floating point numbers and those kind of things, like back when they had the arithmetic logic units that started kind of coming in. So there'll be stuff like that. There'll be stuff with, potentially with GPUs. You'll have similar kind of processes going on. You'll have stuff with parallel stuff, with hyperthreading, all those kind of things, can occur. And depending on the chipset, you may actually have to switch and do it differently to get all the efficiency out. So that's what's happening here. It's hardware optimizations specific for the chipset on which you're compiling.
The other is code generation, which is the point where the intermediate version produced by the machine-dependent optimizations is converted into the actual output language.
Right. So it optimizes and then it does it at this point, because all the optimizations that it can do are kind of out of the way.
So basically, the compiler front end is sort of checking for issues.
Yeah, it's validation and it's prepping.
Yeah. The middle end is huge on optimization. Like we spent most of our time there talking about the various types of optimization. When you get to the back end, you've got kind of your last little bit of optimization. And then the last step in this is, hey, the whole point of it is converting it to another language. And so this is where you generate that. So we've checked it. It's working right. We've optimized it to the nth degree where there's no more possible optimization that can be done. Now we're going to generate the new code.
Yeah. And I think the other thing that we probably kind of left off in that middle was that those are machine independent optimizations. It's like mathematically, this is not as efficient as it could be. Whereas the back end is like on this chip, it's not as efficient as it could be, because there may be caches. There's a lot of stuff going on.
Mm-hmm. Yeah, that's sort of what I was getting at with, like, you've got the abstract optimizations there in the middle, and then you've got the specific optimizations here. And now we're getting into that. Now that we've optimized at every level possible, we're going to generate the code. And it's rather complicated as well.
Yeah, so a lot of decisions about storage and scheduling happen during this phase. So like where stuff goes, like which CPU register it needs to go into, where it is in the cache. This is where like your L2 cache gets controlled. This kind of thing, by the way, is why like a lot of your high level languages, you can't get the performance out that you can on a lower level language, because it's really hard to do this well in an automated fashion and always have it work.
Also, this may involve rearranging the order of instructions in a program to something that is basically computationally equivalent, but has less risk of kind of stalls in the pipeline.
Yeah, so this is very similar to deadlocks, right? Like I'm writing something and I need to read it. and there's multiple pieces interacting with it, if that goes in the wrong order, you either get a bad result or you just can't get a result.
And none of us have ever had that problem ever.
Yeah.
Even at much higher levels, we've not had that kind of a problem. And imagine the stress. I'm just thinking of some times that I had to write something to the database and later in that same API call, build a report from what was written to the database.
Right. And it has to be committed to the database before you get it back.
So I'm just thinking about all the complications there. And that's really abstract and high up. So think about all those headaches, but much more low level and specific to individual chipsets.
And there's no guards. That's the other thing, right? Yeah. Like with a database transaction, you can say, hey, I'm going to wait for this transaction to complete and to be in there before I read. Or, hey, I'm willing to take this level of dirty reads.
Yeah.
Right. Whereas with a CPU, when you're doing that, it's just it's always a dirty read.
Yeah.
You just got to have some method to say, how dirty is it yourself? You're making the heuristic.
Yeah. Yeah. No, it's I'm just thinking of where I've had to deal with that, and I couldn't this is such low level. Dealing with that kind of stuff here is crazy.
Yeah, and basically, we were talking about the pipeline stall thing, and that occurs when you're trying to avoid a hazard. So again, the dirty read type situation where you could corrupt data.
Yeah.
Because you got to also bear in mind, a lot of the stuff that's happening at the CPU level isn't your computation. It's not you going, I'm filling in a report. It's this thing going, hey, what's the next memory location from here? And so you can screw up all kinds of stuff. You can damage hardware at this point. And so they're super careful.
Yeah. So those things, those hazards occur when the next instruction can't execute in the following clock cycle, or it'll execute with a bad result, like you're talking about. Clock cycles. I've been learning about those. That's a whole. We didn't even get into that.
Yeah, and so you'll see stuff where it's like, hey, I need to load this and do this instruction, and then the next instruction isn't dependent on it, and so it loads the first one, and then starts loading the second one on the next clock cycle, and then does the evaluation for the first one, and then does the evaluation for the second one because of the amount of latency.
Yeah.
And that's completely normal for these kind of programmers to deal with. And that is not normal for the rest of us normally.
Right. That makes perfect sense. Basically, these hazards can result either when the timing issues that we're talking about with the CPU aren't considered, or when timing issues around when data should be read or written aren't considered. And we've kind of given a couple of high-level examples here that's just... It's really a lot. Think deadlocks and race conditions, which is what we've been talking about, but at that super low level.
Right. And things where you have you're trying to read out of a register to put it into memory, and the next instruction, is happening while you're doing that read, and it overwrote what you had in there. Right. I mean, there's just there's a lot of stuff that those people really deal with, and we should probably be pretty grateful. The other thing that can really burn you is memory addressing. When stuff is allocated, where is it allocated? How is all that stuff managed? Even if you're doing a not so high level language like C++, you're not ever really saying, hey, I want you to create, give me a chunk of memory at this location. You're saying, hey, give me this amount of memory somewhere. Well, the somewhere gets allocated here, and that gets figured out. It's just, slots and pipes type things. It's not. Yeah.
And you say in the C++, give me this size memory. This looks at it and goes, all right, it probably for optimization purposes has to go, okay, where do I have that amount of memory, and where is that not going to be a problem? Because I think of, and this is a crazy example, but I think of ordering concert tickets. When I order tickets for a concert, they really don't want me to buy 3 seats next to each other when there's 4 seats in a row there, because then they're going to have a lot of trouble selling that one seat.
Right. And so it deals with like memory fragmentation and all that. I mean, the OS gets a lot of this, but bear in mind, this is what the OS is running too.
Yeah.
And it's going, okay, I'm allocating memory at this location, and they've got to have some way of knowing that that's allocated. And you get this low level, like all the safeguards that we're used to are just not there.
Code generation also generates a lot of other useful artifacts. Like the information that your debugger uses may also be generated during this part of the process.
Right. And so you have debugger symbols, when you're going through and you're debugging, that's basically like, I am currently at this location. And, this got basically kind of an ID or a symbol, and you can look it up in the PDB and it says, here is the line number and the file. It is basically the gist there. And so when you're stepping through, you can actually see what just executed, and you can get all that information, at the current execution point. And that's really, really important. I do know a lot of people that really don't like debuggers, and so they'll just log everything. Now, there's a reason for that, right? If it's me or you, that's kind of, okay, you're a little weird, but whatever. But if you're, I don't know, Linus Torvalds, or you're some guy that's writing a debugger, and you know how that particular sausage is made, you don't trust the guy writing a debugger because he's like you, at which point you just log. But, for the rest of us, this is a really important thing that happens during the code generation. It's essentially, the PDBs, you could almost look at them as another representation of your program. It's just not really executed by the CPU.
That makes sense. So guys, there is a lot going on in the process of converting your high-level code into something that the machine can actually use. While you may not have to worry about this stuff on sort of a day-to-day basis, it is really important to understand what's actually happening to convert your code into something that the machine can use. I know we talked about a situation that happened to me just earlier this week, where having that understanding helped me figure out, oh, hey, it's in the wrong mode. That's why I'm not able to actually debug this and see what's going on. In a lot of cases, understanding what is going on under the hood can help you troubleshoot certain kinds of performance problems and other weird issues in your code. Additionally, the understanding of how compilers work can also be informative when dealing with certain kinds of problems in that higher level code. And guys, that pretty much wraps us up. Before we close everything out, Will, what do you have for us this week for Tricks of the Trade?
Well, one of the things that was super valuable in this episode and in a discussion of assembler and compilers and all this low-level stuff is realizing that all the safeguards that you have were put there by somebody else, right? Like the things that protect you from damaging yourself by overwriting memory when you shouldn't overwrite it, or having deadlocks, or having scheduling issues at the CPU level. All that stuff was written by somebody. There's not a scenario that occurred just in nature and this happened. This also tells you that as you get higher up, there's going to be cases where those things have bugs. And you'll see this periodically with processors. In fact, the Intel chipset and the AMD chipsets recently had some pretty nasty issues that resolved, that were basically around timing. And this was like the speculative execution of code and some of those kind of things that are really, really deep, difficult tasks, that the processor and the compiler get involved in. The rest of us didn't have to worry about it, except for the fact that we all had to patch. If you don't know that this stuff exists, or you don't know how it works, you're not going to understand the value of that patch. So you have to figure out at some point, how do I get the experience with these really, really difficult things so I can understand how the computer works without all the safeguards. Once you do that, you're going to understand how the safeguards work that you're interacting with and when to try to get around them. You don't want to just copy code off a Stack Overflow that's doing stuff like screwing around with, the way the compiler, interacts with a CPU, right? Like you don't want to do that yourself unless you really know what's going on. And it's worth learning all this stuff to do that. This is why a lot of companies won't hire you unless you've got a CS degree. This stuff is why. It's not that it's that useful most of the time, but when it is useful, you've got to have this knowledge. Now, that said, you don't have to get a CS degree to do that. You can do it on your own. You can learn how OSs work. You can learn how kernels work. You can learn how CPUs work. And we're going to get into more difficult topics around this kind of stuff as we go forward with this podcast. We're trying to kind of step it up a little bit more. However, it still is really, really important. So learn how the machine works. And that's all I got.
Stand by for Titanfall.
If you have a question or comment, please email us at neckbeards@CompleteDeveloperPodcast.com. Our theme music is an excerpt from Stand By for Titanfall by Pure Bells, available on SoundCloud and licensed through Creative Commons.
The intro music for IoTs is Hillbilly Hip Hop by Jason Belcher. For references, show notes, and to sign up for weekly emails with extra tips and insights, be sure to check out the website at CompleteDeveloperPodcast.com. You can also follow us on Twitter at CompleteDevPod and like our page on Facebook to keep up with news about the show. Catch us each week as we broadcast live, talking about what's going on in the tech world and answering listener questions.
Learn more about all of our shows and groups by going to CompleteDeveloperNetwork.com, where you'll find links to Junior Developer Toolbox, Developer Launchpad, and our other communities. Thanks for listening. See you next time.